Hi students. In this lecture, I am going to discuss problems based on rolling motion. So in the last class, we have discussed what is rolling motion and some important points regarding that. Let us see problems based on that. So the first one, a uniform wheel of radius Kepler is set into rotation about its axis at an angular speed omega. This rotating wheel is now placed on a rough horizontal surface with its axis horizontal. Because of friction at the contact, the wheel accelerates forward and its rotation decelerates till the wheel starts pure rolling on the surface. Find the linear speed of the wheel after it starts pure rolling. So initially having only angular means having only rotation, right? Placing on a surface which is rough and horizontal. So we have to find the speed when it starts a pure rolling. Let us see how to solve it. See the question given. It is a wheel. So wheel means we are taking as a disc. It has only rotation that is now placed on a surface which is rough and horizontal. This is now surface. Placing on surface like this. You can see for bottommost point velocity. For bottommost point velocity is because of rotation r omega, that is left side, and contact surface, it is ground, it has zero velocity. That means the velocity of contact point is not same as that of contact surface. That means it is now slipping. It is now slipping. So it has velocity backward, or you can say left side, with respect to the contact surface, because friction opposes relative motion. That means now frictional force will be right side. I am repeating. With respect to ground, for contact point, velocity left side. And friction always opposes relative motion. Therefore, friction acting on the wheel by the ground is right side. Okay. So frictional force will be right side. And you can see this is now slipping. Since it is now slipping, friction will be kinetic. It is F suffix K, okay, which is equal to mu K into normal reaction. And now in this case, normal reaction equal to mg, because mg downwards, normal reaction upwards. Along vertical, there is no motion. Okay, right. Now focus carefully. When we are placing this wheel on ground, for center of mass, there is no velocity, right? And if you focus on the body horizontally, net force is frictional force. Therefore, now center of mass is having acceleration, which is a constant, because frictional force, which is now kinetic friction, that is a constant. Mu k is a constant, n is a constant. So net force on the wheel, that is along horizontal, which is a constant. That means ACM is a constant. ACM is a constant which is equal to Fk by m. And you can see initially velocity of center of mass. I am taking it as UCM, U. That is now 0. Acceleration constant. Then VCM. VCM is equal to U plus AT, U value 0, A value Fk by M into T. If we know at what time rolling starts without slipping, then we can find its velocity. Okay. Next. Now focus carefully. About center of mass. About center of mass torque equation. Because of gravity, I'm making diagram here once again. First of all, focus a free body diagram. mg vertically downwards. Normal reaction vertically upwards. Frictional force right side at the contact, which is a current. If you focus torque equation about center of mass, so here what we are doing is always we consider motion of center of mass. Center of mass always having translatory motion. So for center of mass, we consider force equation. Next, we take rotation about center of mass. That means we are going to take a torque equation about center of mass. Okay. Now see carefully about center of mass torque equation. Because of gravity, because of normal reaction, there is no torque because these two are passing through center of mass. Now torque is only because of frictional force. And you can see the sense of rotation means torque. Because of this force, torque will be anti-clockwise. But remember, omega is clockwise. Okay. That means here alpha will be anti-clockwise. Okay. Because net torque is anti-clockwise. Alpha is also anti-clockwise. But omega is now clockwise. That means gradually omega decreases. Omega decreases. And frictional force right side. Speed of center of mass gradually increases. So speed of center of mass increasing. Omega is decreasing. Okay. So now we are focusing at what time rolling starts without friction. At what time rolling starts without friction. Since it is rolling on ground, VCM should be equal to R omega. Okay. VCM, that is how much? Fk by M into T. VCM equal to R omega. But coming to omega value, what happens is now it is a keep on changing. We can write from kinematics of rigid body, omega 2 is equal to omega 1 plus alpha. Now in this alpha clockwise, sorry, omega clockwise, alpha anti-clockwise. If you take clockwise a positive, anti-clockwise will be negative. That means now omega, or I'm taking as omega dash, that is equal to omega minus alpha. Okay. After some time, what happens is VCM is equal to R into omega dash. In the place of omega dash, omega minus alpha. Okay. This is now condition for rolling without slipping because it is now rolling on ground. That's why VCM equal to R omega. So VCM Fk by M into T. What is alpha value? See carefully. Torque. Torque equal to Fk into R, that is a torque, which is equal to I into alpha. Since it is now wheel means disk, I value about its own axis is mr square by 2. Therefore, alpha value mr square by 2. It is now 2 Fk upon m r square. I'm writing here m r square by 2 into alpha. 1 r gets cancelled. 2 Fk by mr. Okay. It is 2 Fk by mr. That is alpha value. Now substitute that in this one. VCM. VCM is now Fk into T upon M, that is equal to R into omega minus alpha in the place of alpha. 2fk by mr into T, that is equal to, take R inside, it is R omega. When you're taking R inside, here R gets cancelled. Remaining is now 2fkt by m. Now take this value left side. It becomes now 3fkt by em. Cross check once. Taking R inside, R gets cancelled. 2fkt by m. Taking left side, 3fkt by em. So from this, see what is the time? It is mr omega upon 3fk, right? Now substitute this in this one. VCM equal to, take this time in this one. Then see what happens. Mass gets cancelled, Fk gets cancelled, right? What else left? VCM is equal to Fk by M in the place of T, M R omega upon 3 Fk. Fk gets cancelled, M gets cancelled. It is now R omega upon 3. That is velocity when it starts rolling without slipping. Okay. Next, see what we can do. Same thing we can calculate by using conservation of angular momentum. It is just a single step, but we can practice in both the ways. Means initial days we can practice by using, this is now using kinematics. Okay. Now see how to calculate directly by using conservation of angular momentum. So first we have to focus. To use a conservation of angular momentum, net torque on the system must be zero. And we have to focus about which point net torque zero on this wheel. Okay. Now see carefully. Take here in this diagram. In this diagram. In this diagram. First we have to find a point about which net torque on the wheel is zero. So if you observe, for example, I'm taking this line as x-axis, okay? I'm taking this line as x-axis. Right? Focus now. If you take any point on this line, so since we are taking this is a wheel, okay, only one point will be in contact with the ground. And that point will be always on x-axis only, right? That point, the contact point will be always on x-axis. If we choose any point on x-axis, if we choose any point on x-axis, see carefully, I'm taking a point on x-axis, it can be anywhere. With respect to that point, I'm focusing now position vector for center of, it is position vector of center of. Now see carefully here. This is R bar, right? That is R bar. Because of normal reaction, about this point torque will be. Just see carefully, about this point torque because of normal reaction. If you apply force in this way, torque will be anti-clockwise. See carefully about this point. If you take a torque because of normal reaction, it will be anti-clockwise. And about the same point, if you take means R bar cross F bar. Okay, torque is R bar cross F bar. This is R bar. and this is F bar. So curl fingers of your right hand, R bar, F bar, normal reaction like this. So curl your fingers of right hand, placing on R bar towards force. Then curling fingers will be anti-clockwise, right? So torque because of normal reaction is anti-clockwise. And if you see torque due to gravitational force, again R bar same, but mg is now downwards. Now curl fingers down. Then fingers are now curling clockwise of right hand, right? Then it is clockwise. So because of normal reaction, anti-clockwise, due to gravity clockwise. For both R bar same. And N and mg, both values are same, directions opposite. So when you are taking R bar cross F bar, R bar same, coming to F bar, values are same, directions opposite. That means torque due to normal reaction is balanced by torque due to gravitational force. Okay. Now remaining is the frictional force. And this frictional force is passing through this point, right? Frictional force acting at the contact. And this force is passing through this point. That means because of frictional force, no torque is acting. That means now net torque on the wheel about any point on x-axis is zero. So about any point on x-axis, we can consider angular momentum of the rigid body. This is our final conclusion. We can consider angular momentum of the rigid body about any point on x-axis. Right? So let me write here conservation of angular momentum. It is LCAM. So initially, this body was having only rotation. Okay. And rotation is now clockwise. Only rotation. And we have learned that because of rotation, angular velocity is I omega. So we are taking about axis of rotation. Okay, about center of mass. Since it is wheel, mr square by 2 into omega. This is now clockwise. Let us take clockwise as positive. It is a complete our choice. So I'm taking here clockwise is a positive. Okay. That is equal to. After some time, this will start rolling. Okay. This will start rolling. This will start rolling. Say once. Right. Now, initially, it was here, somewhere here. After some time, the wheel will be somewhere here. Assume that this is now location of the wheel when rolling starts without slipping. When rolling starts without slipping. Initially having only rotation, right? So we have taken point somewhere here. This is now position vector of center of mass. You can see position vector of center of mass is keep on changing. Okay. But when we want to calculate angular momentum, so what I'm saying here, while taking L bar equal to R bar cross P bar, we can focus first of all magnitude, that is M into VCM. We are focusing because of translation. Okay. So for focusing VCM, M into VCM into perpendicular distance. Okay. And how to get it? Imagine a line passing through point parallel to P bar. This is now perpendicular distance, which is equal to R. Okay. And if you take now, this is R bar across P bar. So take your fingers off your right hand. Take fingers of your right hand, curved fingers, by keeping on R bar towards P bar. Now it is a clockwise. Means because of translation, angular momentum is clockwise. So I'm writing here M into VCM into R. Okay. Next rotation. It is a still clockwise. So it is a plus I omega. I value mr square by 2 omega. Omega how much? So we have taken v equal to r omega. We have taken VCM is equal to R. This is omega dash it when it starts rolling without slipping. So in the place of omega dash, I can write VCM by R. So I omega dash VCM by R. Okay. So angular momentum finally. Now throughout we can cancel mass. We can cancel R also. R and one R left here that also cancelled here. Remaining is now VCM plus VCM by 2. It is now 3 by 2 VCM. That is equal to R omega by 2. 2 gets cancelled. So VCM is equal to R omega upon 3. Like this, we can calculate by using angular momentum conservation. This is by using kinematics. Okay. Suppose in this problem, if you want to find time taken by using this equation, so by using LCAM, first we get VCM. And once VCM is known, we know that VCM equal to ACM into T. Then we can find at what time rolling starts without slipping. Okay. Next, in the same question, they can ask like, find how much work is done by frictional force. Okay. Means until rolling starts, how much work is done by frictional force. And you can see here, because of friction, energy is lost, right? So initially kinetic energy how much? And finally kinetic energy how much? Okay. So final kinetic energy minus initial kinetic energy, that gives work done by frictional force. Because you see carefully, if you want to take work energy theorem, W net is equal to delta K, right? How many forces are acting? Gravity, normal reaction, and friction. Because of normal reaction, no work is done, right? Because of gravity, no work is done. Now work is done only by frictional force. That means by friction, work done is equal to delta, right? So like this, we can calculate work done by frictional force until rolling starts. And we can see here one more thing. Once rolling starts without slipping. For a contact point, there is no velocity. For contact point, no velocity means there is no friction because VCM is a constant. VCM constant means there is no friction. Okay. That means from this we can conclude that on a horizontal surface, rolling is a possible. Even surface is a perfectly smooth because in this no torque is acting means net torque zero, net force zero. So frictional force. So once rolling starts without slipping, when surface is a horizontal, no frictional force acts. Okay, that means on horizontal surface, rolling is a possible even though surface is perfectly smooth. This is what we can conclude, right?